Hello? All right. Hey, if everyone wants to take their seat, we can get going again. All right. My name is Aaron Durbin. I'm going to be talking about doing an x86 port for like a chipset or CPU to coreboot. Some of the information in the deck is going to be somewhat repetitive, I guess, because we're going to be covering similar things that Duncan had touched upon before. But hopefully the repetition will breed familiarity for some of you. So we're going to cover early boot flow, touch upon the resource handling and the resource allocator within coreboot, device probing for devices that are probable. We're going to do or touch upon multiprocessor initialization and then a little bit of mainboard interaction. And I hope to not go too long, and then so you guys can ask questions if you care. But you'll at least see somewhat of a similar pattern here. Down below are, with footnotes, are paths within the coreboot repository that touch upon some of the topics so that you guys can go back and look at the source code and match up with the slides. I don't recall if Duncan did mention this, but these slides are published currently, and somewhat they will be. In either case, they'll be published publicly, and you guys can go back and review as need be. So for the early boot flow on x86, so there is this concept of boot block, ROM stage, RAM stage that Duncan did talk about. For x86, the boot block is execute in place. It uses ROMCC, as Duncan noted before. It's a very constrained environment, and it actually depends on the amount of registers available, so that if you're trying to compile C, you know, basically how many registers do you have to spill, because obviously you have no stack at this point. But its main goal is to get into 32-bit protected mode and then find ROM stage and CBFS and then jump into it, because ROM stage is actually execute in place as well. If you guys go digging, you can find a really interesting implementation of a CBFS parser in assembly without using the stack, so that's always a fun one. The ROM stage, this is specific to our Chromebook x86 devices starting from Haswell. And what we actually do, starting with the Haswell devices, is that we actually have ROM stage split into two parts. The first part is where we have to set up cache as RAM, in that we use the cache as the backing store for, like, we actually have RAM to write into and read from. I believe there's a number of Intel people here. If you could go to the bean counters and find some die space for SRAM, I would be ecstatic, and I'm sure quite a few other people around here would be, and we would buy you many, many beers if that's your drink of choice. So please push that internally as well, because I cannot imagine that an SRAM is that much die space versus 0.001% of better branch prediction. But anyway, that's my plug. So we don't have SRAM, we have to set up cache as RAM. And so the way that works is it's an assembly routine. We get our caches RAM up, and then we have C code, and we run. And within that, we run the memory reference code that's provided by Intel. And then the second part, which it can be utilized by any other sort of x86 platform, but typically it's not, is that oh, sorry, I confused myself. We'll go through, this is let me take a step back. So this is the in caches RAM mode. This gives an example of how we actually have, this example is from our Bay Trail internal reference platform called Ramby. And this kind of gives an idea of some of the things that we do and how it's actually structured within the code. And the reason for some of this is that we want the chipset to drive a lot of the logic so that when we're doing a mainboard port, we don't have to do a lot of things that have to be known and duplicated. So saying, okay, chipset, go do this now, now go do this now. It's more of a, we provide a few entry points into the mainboard. In this particular case, there's a single one, which is called a mainboard ROM stage entry. And we do that is because one, we don't want to use global variables in the cache's RAM. If you go digging through the coreboot code, excuse me, you can find examples of the infrastructure using it, but once we tear down cache's RAM, and since the ROM stage is linked at execute in place with a known address space, those addresses disappear. So you don't really want to use them because it can cause quite a bit of an issue of usage after the fact. So what we do is we use the cache's RAM for the stack, and it's a fairly large stack. But so the reason why this looks kind of like somewhat convoluted code is that we use the stack and structures on the stack as the main configuration for doing certain things that may be mainboard specific. And because of that, since they live on the stack, we have to start in chipset code, go to the mainboard code. It can drop its configuration structures on the stack and then pass back into the chipset code itself. So that's where it can be a little bit convoluted, but it does, if you've seen it in this particular case and see how it's actually used, it makes for the mainboard ports to be a lot easier, I guess, for lack of a better term, but there's not as much knowledge or needed knowledge with respect to how something is implemented in the chipset portion of things or the CPU portion of things. So that I think that's a good trade-off for not having to complicate matters when we're trying to do different main boards. So, excuse me, so the second part, as I noted, is that we've ran the reference code, so we have RAM that we can use. So we don't need cache's RAM anymore, it can be torn down. As I alluded to before, not all main boards or chipsets actually have this sort of second stage. They kind of tear down cache's RAM, and then they run code that will go search through the CBFS for RAM stage. But in this particular case, as Duncan talked about as well, we have vboot. And with the Haswell, starting with the Haswell devices, we actually we verify boot RAM stage, where before prior to that, we were only able to verify boot the bootloader. And because of this, that means because of that, we can actually we can update RAM stage outside. Once the device is shipped, we can make changes. So if there's a firmware bug of some sort, we can make a change. It can be pushed out. It could fix a particular device. If there's like some issue in the ACPI code or something, it'll handle all that, which is a very nice property. And so in order to meet those goals, that we have to do vboot and ROM stage. And so we essentially drop down out of cache's RAM, tear it down, and then we call back into ROM stage code again, which is execute in place, but we actually have RAM to work with, and we have a stack that we can use. And when I was discussing about the cache's RAM globals and how that actually works, when we come back out, since the ROM stage is still linked at thinking that it actually has a data area in some portion of the physical address space, it doesn't any longer because cache's RAM's gone. So that's where you don't really want to ever use global variables. There is a mechanism that we have in place to transition cache's RAM variables across that boundary, and some magic heuristics for determining where a pointer should actually live. But if you want to dig into the guts of that, you definitely can. But this picture should look somewhat familiar because we have the 3 copies of RAM stage that are always in our systems, and 2 in the read-write A and 2 in read-write B. And then we have the fallback in the read-only portion of our SPI ROM in CBFS. Okay, so RAM stage, after we've done a vboot verification, we then we will then say, oh, we need to go with read-write A, for example. That will get loaded from that portion of the SPI ROM into RAM. Its entry point is at _start and C start under the x86 portion of things, and that calls main, which main is the hardware main, which is the boot state machine that Duncan had covered. The device tree is mentioned yet again because it does play a fairly central role in how we bring up x86 systems. And so here's the list of things that should look all familiar to the people that have had to deal with booting x86 systems and the pain that it brings. Oops. Okay, this is a slightly different presentation of the boot state machine along with the various callbacks. And so it does look repetitive, but I actually have a copy of this stashed in various email accounts because this is the cheat sheet I have to go back to all the time. But it helps it helps in actually knowing when something happens when coreboot boots. So let me see. Okay. So we mentioned the concept of a chip in device tree, and a chip is an abstraction that it holds a collection of devices in this sense. And there are special devices that the sconfig tool that was previously talked about that parses these into C structures that gets compiled. And so, sorry, excuse for the kind of muddled slide, but there is a lot of information that I'd at least like to point out that are kind of weird if you aren't familiar with them. In that, so on your upper right-hand corner here with the SOC init that then calls Bay Trail init pre-device, that's actually done by way of the SOC Intel Bay Trail chip. And that then so basically that is allowed, so for every chip that's in the device tree, we call the initialization function that's associated with that particular chip. And that's where we start off on doing a few things for, at least in the Bay Trail land, of doing things very early before we go through the device probing. But the key point is that there's also within the struct device within coreboot, there's different paths types, which are essentially enumerations for the type of device. So in this particular case, there's device path cluster and device path domain, and it's kind of boilerplate if you look in any chipset, but you actually have to bind operations at runtime for handling these devices. In the source SOC Baytrail chip.c, there's actually some code in there that you see that, oh, I'm enabling this device, which in this case is a CPU cluster, and it has a path of the device path CPU cluster. So you actually bind the operations for each of those sort of or I guess bus sort of devices at that level. Additionally, there are CPU IDs that bind to devices with drivers. So there is this concept of drivers within coreboot, and that you need to make sure that those DIDVIDs, for example, for the PCI, and then CPU IDs match up, or otherwise you will wonder why your code didn't get called, thinking it should have, but oh no. Yeah, so that's kind of a gotcha in that if something is not working the way you think, always go back to double check this sort of where this particular driver or code would actually be bound to a device. So there's a couple examples in there. So there are, at least for x86, there's two main resource types. There's the port I/O and memory physical address space. And these resources are very valuable in the sense of they're required for booting, obviously, but also because of the way that MTRRs are set up and done. And there is there's support for both fixed and allocated resources. And what it means by that is if we, for example, PCI devices are probable and they have a set bars, that you can allocate memory mapped I/O onto for those devices. But there's also registers that need to be set up that set up different memory mapped I/O spaces that aren't in a standard in any particular way. So if those were set up at a certain address, they need to be set up again, but you also need to indicate to the resource allocator that this memory range cannot be used for dynamic allocation for other I/O resources. And so if we go back to here, so the read resources is actually where you need to ensure that all of the resources that your particular device uses is set in there. And in Duncan's slide, there was a PCI dev read resources, which is the common one for any standard PCI device, which their bars can just be allocated dynamically. If you have a special device, so for example, the LPC bridge on Intel parts, there's usually a lot of other fixed bars that are not probable that need to be set up. And those, when they're set up, also need to ensure that they are carved out of the address space so that we do not collide in the resource allocator. And what there are other attributes. So if, PCI has prefetchable address space or prefetchable memory types, and those are set accordingly. But the key with respect to how these are used for MTR code is that we need to set, register, I guess, all the resources in read resources before they're set in set resources, because set resources is where all the dynamic allocation happens. And after that, typically, is when MTRs are set up for the system boot. And the MTR code uses the resource map to produce an address space so they can actually then allocate MTRs from. So there's a couple of helper functions down at the bottom that if you just, I don't have an example of what it normally looks like to create a resource by hand, but it's well, not quite a bit, but it's a little more code than you'd want. There's a couple of helper functions, so if you just say, hey, like if you're talking about your North Bridge, for example, or anything that's handling the DRAM, if you say RAM is here, I've got a chunk of RAM here, a chunk of RAM here, that'll get carved out. If you need to reserve RAM for some reason, there's a reserve RAM resource, and then memory mapped I/O resource is essentially a shortcut for fixed memory mapped resources. Okay, so MP initialization, like I said, this typically happens after resource assignment. At least it doesn't have to. There's a number of different games you could potentially play, but the current model that we are abiding by and that we've done is that resources have been assigned by the dynamic allocator. Everything's set up. Then we set up MTRRs, and then we bring up MP or APs. In coreboot, it's upstream as well, and in our repo is that there's a notion of an MP flight records to basically structure different steps of bringing up MPs or APs, and it allows for a little bit of flexibility, or quite a bit of flexibility actually, but it also, and to give you somewhat of a kind of an example, so you typically need to bring up the APs, depending on what chip and what specification the BWG may say, you have to load microcode before you ever do SMM or set up caching or what have you. This particular code actually, there's a whole library that will then do the init CPI sequence, but it also stashes away the BSP's current MTRRs and then says, when you come up, load, it also has a pointer to microcode. It loads microcode in assembly. Then it sets up all the MTRRs, caching's enabled, and then it comes into C code. And so basically we've met those sort of previous requirements that are normally set in that sort of environment. And then of course there's the infamous SMN relocation on Intel x86 systems. And for Haswell, it has an awesome property actually, is that you can do parallel SMM relocation. For the Bay Trail parts, that was omitted. But But what this allows you to do is that to compare and contrast those two things, both the Haswell and the Bay Trail stuff, or the Bay Trail support code, can use these similar flight records and do specific things when it's actually doing SMM relocation. And then there's this MP initialized CPU is actually calls into some common infrastructure that goes through the driver binding for CPU IDs and runs the various common paths for initializing that part. And with this particular example, there's all of these are blocking the AP, so essentially the BSP can run, and then when it's done, it actually then releases the AP. So there's barriers for various things. You can step sequence through everything rather quickly in that regard, and without having to really kind of think about it and redo it all over again. So that's a common piece of infrastructure that's available, and is an example. So back to somewhat of the device tree thing and device specialization. At least from our approach, we do not enumerate every possible option that could potentially be available for changing something in the chipset, because I'm sure many of you who are from Intel and then have read through the reference code and have seen the myriad of options that can be a little overwhelming. Honestly, at least with very targeted devices, we don't make everything an option. We basically, at least the approach is that we assume it's going to behave a certain way, and then we can always pull back an option later if someone needs it. So it does not, we don't have to go through the whole litany of trying to figure out, oh, is someone going to want to do this? Is someone going to do that? We'll just, bring that in when it's needed. But this particular example, what it's showing is the mapping between the device tree and then what happens in C code. And what I'd like to pay attention to is that this is all done by humans. The device tree is written and says there's this register which maps to a field in a C structure. Well, you have to make sure that C structure exists with that field. There's no automatic C structure generation for this particular case. So be warned in that if you think it's just going to show up, it's not. You have to make both sides match. So this example talks about some of the SD card controller capability overrides that we have in there, and then the ability to put certain of the PCI devices into ACPI mode based on these settings. And this would, on the left would be what you would see in your main board device tree.cb, and the chipset code handles the various options. Oh, so here we go. Similar to what Duncan's example had. For each device that's associated with a chip, and all devices are associated with some sort of chip, you can see that the chip info is a pointer to the config that is associated with it. So I should say all devices that are in the device tree are associated with the chip. So if you go and probe PCI bus and you have like a Wi-Fi card on the other side of a root complex or something, it won't have a chip info associated with it. But don't hold me to that, that's just what I think. Anyway, and this shows how we can get the config off the device, and then we can interrogate the fields within the config and then do the appropriate things. And lastly, I just wanted to note that yes, we do support ACPI. AML is ran through the ASL compiler, but we also allow a little bit of dynamic AML generation. There's some libraries to do that. I would note that somewhat different from, at least for Intel's reference code and UEFI and stuff, that there's no interpreter and then basically a way to basically break up and rewrite changes or interject stuff into the AML code itself. That does not exist in coreboot. So that is what I have. Apologies if it's too short, but I was not sure the actual audience would be. And so really what I'd like, if people have had the opportunity to take a look at coreboot, and if they have their own ideas, questions, or whatnot, I'd be happy to field those questions, if anyone cares. The question was, when you're starting a new board, what is your method for bringing it up? And so I assume you're also referring to if you're doing a new chipset as well. But yes, they go hand in hand in that regard. If you look on our within our coreboot repo currently for Bay Trail and Ramby, you can kind of see the at least how we ended up attempting to bring that up. And it was not work in a corner for months and then land every single thing. So you kind of onboard different pieces. It's like, oh, well, I can get through cache's RAM. Okay, this is good. Let's get that infrastructure in place. Oh, I can get into RAM stage, get that in place. Oh, I need to start adding these device drivers and that sort of thing. What you'll find in there is a remnant, I think it's gone now. There was a placeholders.c under Bay Trail, which was basically, there's pieces of code or symbols that needed to be resolved to link RAM stage that we didn't have support for yet, right? So it's basically, it was a dumping ground to make sure that we could still link and run through, essentially. But yeah, it was a very evolved sort of process. It was not like whole hog drop down sort of a thing. So it's kind of, you know, bring this part up, and keep moving forward from there. Any questions from the ARM folk? Any chuckles from the ARM folk about the things we have to go through?
So the distinction in coreboot for a main board versus a chipset, I would assume this is to cover, even in the case where a chipset and a processor are the same thing, as in the case of an SoC, the main board is then what is the model of how you wire things to the SoC, so the difference between, for example, Falco and Heavy would be a main board?
Yeah, and Sean's going to definitely touch upon this later. But the question was, what differentiates two devices, essentially, that could use a common CPU chipset? And that all that code, we like to make sure it lives in the main board. And I'm sure Sean's example, will speak to this, but a good example, the first thing that comes to mind when anyone talks about two different main boards is, well, are the GPIOs mapped the same? Are they connected to the same devices? If I use the same config, am I going to short out every random thing that's on the board? And yeah, that configuration, or at least the metadata about each particular GPIO would live in the main board, and like if it has a device or not. For example, if there's a particular device that has a touch screen and it would be connected to this, I2C controller, and this other device doesn't have one. Well, you can shut that whole controller down in the device tree, and that's how we typically handle that. All right.